Okay. Last time we talked about the generating functions for cones, right? So we talked about the enumeration of the lattice points in an arbitrary cone, and we did it in 2 steps. So the first step was to do it for simplices, and so we gave a very nice, for simplicial cones, so we gave a very nice explicit formula for the generating function for a simplicial cone. And then we said that if you want to do this for any other cone, then any cone can be triangulated into simplicial cones, and so you can just kind of cut it, like I said, just triangulate, right? So you just triangulate it, and you kind of add up the pieces and make sure that you don't do any double counting, okay? By the way, I should be honest with you in telling you that, oh no, I guess I already confessed to you last time that that's an oversimplification. That it is a subtle question how not to overcount. It's a question that can be solved in an example. You can do it, and there is a nice machinery that involves a little bit of topology actually for how you keep track of how much how to not overcount basically. But it can be done, okay? And that basically tells us that we can compute generating functions for cones, and that's fine. But the thing is that that's not really what we care about so much, because I mean, really what we care about the most is about polytopes. But so what I want to do today is to show you that once you know how to do this for cones, then you basically know how to do it for polytopes. Okay? So we're going to talk about how you go from cones to polytopes. So let's say that you have some polytope P. It's the convex hull of, say, V1 up to Vn in Rd. We're going to assume that the vertices, that all the vertices have integer coordinates, okay? So, and remember that our goal for the last week or so has been to figure out how to count the number of lattice points inside P. Okay, and I told you how if you can write down the generating function, then you can count the lattice points. Okay. So here's the trick, and here's the trick basically. This is the trick. The trick is that I'm going to take the polytope. This is P. And again, I'm going to do this trick of going to 1 dimension higher and consider the cone over that polytope. Okay? So the cone over P is going to be the cone that is basically generated by these vectors, okay? So now you should think that basically P is, let's say, d-dimensional. Now this picture is d plus 1 dimensional, okay? And so what you have to do, you should think that each one of these planes that I drew is a horizontal plane in terms of the direction xd plus 1, okay? And so this is the origin. These are the points of height 1, height 2, and so on. So what I'm doing is just putting the polytope P at height 1, and then taking the cone over that. Okay. So I take the cone of each vector with a 1 coordinate in the end. Okay, and this lives in 1 dimension higher. So here's something that's easy to check. That if you take this cone and you intersect it with the hyperplane xd plus 1 equal to t, then what am I going to get? Well, like I said, this is the hyperplane sd plus 1 equals 1. This one is sd plus 1 equals 2. This one is xd plus 1 equals 3, and so on. Okay? And so you can see easily from this picture that the slice here is basically double this polytope, right? This is just the dilation of this polytope by 2. This is 2p, and this is 3p, and this is 4p. And in general, if I intersect with the hyperplane xd plus 1 equal to t, what I get is tp. Well, that's almost true. The only problem is that this lives in d plus 1 dimensions and this lives in d dimensions. So I'm going to say they're isomorphic. Okay. Okay. Now, this is good because remember that our goal was to compute the number of lattice points not only in P, but in all of these dilations of P. Okay? And we call this L sub P of T, and this is the number of lattice points in the Tth dilation of P. So this is exactly the kind of thing that we want. And remember that I also defined the Ehrhart series to be the generating function for this thing from t equals 0 to infinity. Okay. So here's how we're going to do this. We're going to say, okay, well, this is something that I know how to compute. Sigma of the cone. Okay, that's the generating function of a cone. We know how to do that. How many variables do I need for this thing? Well, this cone lives in d plus 1 dimension, so that means that I need d plus 1 variables, right? Okay, and remember that by definition, this is just a sum over the lattice points in the cone of z to the m. Okay, and again, you see that because m has d plus 1 entries, that's why I need d plus 1 variables. Okay. Okay. But now what I'm going to do is that I'm going to say, I'm going to split this into basically, I'm going to do this. I'm going to consider this sum, but I'm going to separate it according to what the last coordinate of m is. Okay? So here I'm adding up those lattice points whose last coordinate is t, and I'm going to do that for all values of t. Okay. So I just split this sum into all these different sums. And the reason I do that, of course, is that I know precisely which ones these points are, right? So if you're a point in the cone of P and your last coordinate is t, then according to this, you're basically a point in TP. You're a lattice point in TP. So I might as well do this summing over lattice points in TP. Right? Now, again, there's a little subtlety here, which is that this M has d plus 1 coordinates, whereas this guy only has d coordinates. So if I write z to the m, then I don't have the whole thing because I lost a coordinate from here to here, which was precisely the last coordinate. But then the good thing is that I know exactly what that coordinate is. That coordinate is t. Right? And so then what I have is z sub d plus 1 to the t. Okay? But you see the beauty of this is that now what we have here in parentheses is exactly the generating function for the lattice points in TP. So this is exactly sigma sub TP of z times zd plus 1 to the t. Okay? So this is kind of a formal computation that, in essence, is saying what you're seeing in this picture. Really what I'm saying is that if I enumerate all the lattice points in this cone, then I might as well enumerate first the ones in the 0th floor, then the ones in the 1st floor, then the ones in the 2nd floor, and so on. That's basically what we're doing. But then you see, the point is that we already talked about how we have a technique for computing this kind of thing. And that means that that technique is going to tell us how to compute the lattice point enumerator of a polytope and all its translates at once. All its dilates in one. Okay? In particular, look at what happens if I take this function and I plug in 1, 1, 1, all ones except for the last variable. Well, then what I have is sum from t equals 0 to infinity of sigma TP of, these are all ones, 1, 1, and then zd plus 1 to the t. Okay. Now, what is sigma TP of all ones? What is it, Dito? It's one for each point, right? Because exactly. Sigma TP of z. Let's write this over here because this is important, and we said it last time, but I think I should say it again. For if you have some polytope Q, then sigma, and let's say that this is in RD, then sigma sub Q of z is sum over lattice points in Q of z to the p. This is a vector, right? Vector, vector. And the point is that if I plug in all ones, then what I'm going to get is a sum over all lattice points of, now this is just 1 to the p, right? So this is just 1. So every summand is 1, and so this is just the number of lattice points in z to the t. And again, remember that what I said last time is that in computing the generating function, we're being more ambitious than we want to be, because if we want to compute the number of lattice points, then this is going to be immediate if we know how to compute the generating function. Okay? So the point is that once I do that, then this is just the number of lattice points in TP intersect z to the d times zd plus 1 to the t. And that's exactly what we're after, you see. That's exactly LP of t. So this is exactly this Ehrhart function. The Ehrhart function of p evaluated at z sub d plus 1. Okay? And this equation is very important. It's, in fact, let me just write it over here so that we remember it. So sigma subcone of p evaluated at 1, 1, z is exactly the Ehrhart series of p. Okay, that's the proposition that we just proved. And so what this says is that if you want to compute the Ehrhart series of a polytope, then that follows immediately if you can compute the generating function for the cone, which we know we can do. Okay, and so that's how you can get from cones to polytopes. So by the way, you'll see that one of the questions in the homework is to compute an Ehrhart series and an Ehrhart polynomial for a concrete polytope, and this tells you how to do that. It tells you if I want the Ehrhart series, well, that follows from knowing how to compute this generating function, which I showed you how to do last time. Okay, so that's one of the possible ways of solving that homework question. Do you guys have any questions about this before we continue? Is it making good sense? Okay, so now assume that P is a simplex. Okay, so not this picture, but imagine if P was a triangle. And that means that when you take the cone, a simplex in d dimensions has d plus 1 vertices. So that means that when you take the cone, it's going to have d plus 1 rays in d plus 1 dimensions. It's going to be a simplicial cone. So cone of P is simplicial. Okay? So in that case, we can compute. So let me remind you of this theorem that we proved last time. Last time we said that if you want the generating function for a simplicial cone, it's very easy. You just have to do this business with the fundamental parallelepiped. You just have to say, count the lattice points in the fundamental parallelepiped. Fundamental parallelepiped. And then divide by. Do you guys remember what you divide by? Basically the rays. You get a term for each ray. 1 minus z to the whatever the ray is. Okay. Now what is the ray? Well, in this case, our rays. Maybe I shouldn't have erased what I just erased, but remember that I called P the vertices of the polytope I called VI's, and the generators of this cone are VI, comma 1. Okay. Let's actually write it. So P is the convex hull of V1 up to Vd plus 1 because it's a simplex. and the cone is the cone of, let's call them W1 up to WD plus 1, where WI is VI with a 1 in the last coordinate. Okay? That's good to have. So then what I have is 1 minus Z to the W1 dot 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 1 minus Z to the W D plus 1. Okay? This is what we did last time. So now what we're saying is that I actually don't want to compute, I don't care to compute this for all these variables Z1 up to ZD plus 1. I can just compute it when I set the first D variables to 1 and then the last variable to ZD plus 1. Okay? So I just plug in ones for all the other variables except for the last one. Okay? So what happens here when I do here, instead of a Z, I have 1, 1, 1. I had Z to the W1, but now you see I'm plugging ones for all the coordinates of Z except for the last one. Okay? So when I do Z to the W1, I'm going to get 1 raised to the first coordinate, 1 raised to the second coordinate, 1 raised to the third coordinate. I get a bunch of ones. 1 to the something, 1 to the something, 1 to the something. And the only coordinate that is not trivial is the last coordinate, where I get what? I get Z D plus 1 raised to the last coordinate of W1, which is what? It's just 1. Yeah? Last coordinate of W1 is 1. So instead of Z to the W1, I just get ZD plus 1. And I get that for this guy, for each one of these guys. So what I get is 1 minus ZD plus 1 Z sub D plus 1 raised to the D plus 1. Okay? Okay. So now the next thing that I want to do is this is the formula that I'm going to work with for the rest of the class. Okay? And so the next thing that I would like to do is I'm going to ask you to forget that Z was a vector, because I'm going to get tired of carrying this subscript around when really here I only have one variable in this equation, right? So I'm just going to forget this subscript. And from now on, Z is just going to be a single variable, not a vector of variables. Okay? Okay. So then here's a proposition. Proposition is that let P be a D simplex with integer coordinates. Okay? Then the Ehrhart series of that polytope is given by the way, you realize that these things are equal to each other, right? The thing that I have here is exactly the Ehrhart series. Right? So the Ehrhart series, I know what the denominator is, 1 minus e to the d plus 1. And I claim that the numerator I'm going to write as h0 plus h1z plus up to hd minus 1, I think. Let me be sure. dz to the d, where h sub I is equal to the number of lattice points in the fundamental parallelepiped pi having coordinates having the last coordinate what do I want to say? With the last coordinate equal to t. I. So you see that actually to go from here to here, it's just a matter of kind of stopping and concentrating and realizing that these two statements say exactly the same thing. Because you see, I mean, of course, the denominators agree. And so all I'm saying is that the numerators agree. Okay? So let's argue that. Well, this is sum over points in the fundamental parallelepiped of, you see, we're supposed to take this vector raised to the power p. But again, what we get is 1 to the first coordinate, 1 to the second coordinate, 1 to the third coordinate, 1 to the dth coordinate, and then z to the d plus first coordinate. So what I get is just z to the p sub d plus 1. So actually, just to make the notation a little bit clearer, this is bad notation because I use z and z. So I'm going to say number of lattice points p in the fundamental parallelepiped having last coordinate equal to I. Okay? And then you basically see here that the number of times you're going to get a z to the I is the number of points in the parallelepiped such that p sub d plus 1 is equal to I. So z to the I appears this number of times. Appears each time that p sub d plus 1 is equal to I. So the number of times it's going to appear is the number of points with the last coordinate. Are you guys happy with this? There's one thing that you need to pay a little bit more attention to, which is this. Why did I stop this sum at z to the d? Because this sum could continue. The reason will be that how high can you have points in the fundamental parallelepiped? Let's think about that. Because what I'm saying is, I mean, look, this is extremely explicit, right? Because I'm saying, just imagine for a second that this square is a triangle. So this is simplicial, okay? And then imagine that I drew the fundamental parallelepiped, which I won't do because I'll ruin the picture, but it's some kind of, maybe I'll just draw a schematic picture of it. Okay? The fundamental parallelepiped is kind of generated by these things, and it's this parallelepiped raised by these degrees. The parallelepiped generated by these vectors. Okay? So what this formula is saying is just count the number of lattice points in the fundamental parallelepiped at each level, and that's your numerator. Okay? And now let's think about that question again. Why did I stop at dimension d? And the answer is going to be that a fundamental parallelepiped in d dimensions cannot go much higher than height d. Okay? That's what I'm going to argue. So this sum stops at degree d because no point in the fundamental parallelepiped has last coordinate greater than d. That's what I'm going to argue, and that's why I get to stop at d in this polynomial. Okay? But I need to prove that this is not for free. Okay? So, but it's not too bad. So what's the fundamental parallelepiped? Remember that we define it to be the combinations of our generating vectors, of which there are d plus 1, where, remember that the coefficients of these, the coefficients that I get to put here, because you're in the fundamental parallelepiped, they have to be between 0 and 1. And also remember that we define the fundamental parallelepiped to be closed in the bottom and open in the top. So this inequality is weak, this inequality is strong. Okay? That's our fundamental parallelepiped. So let's take a point in there. So that means that P is equal to the sum of lambda I, Wi, but now Wi I'm going to write it as Vi and a 1. Okay? And now let's compute the last coordinate of this expression. The last coordinate of P. The good news is that then the V's disappear, right? The last coordinate is just sum from I equals 1 to d plus 1 of lambda I times 1. Okay? How big can this be? Well, each lambda I is less than 1, which means that this is strictly less than d plus 1. Okay? So if P is in the fundamental parallelepiped and it is an integer point, then this is not only less than d plus 1, it's less than or equal to d because it's an integer. Right? And so that's why this number hi is going to be 0 for I equals d plus 1 and higher, and that's why I stop here. Okay. And you see that this tells you that I mean, this is extremely explicit. This really says if you want to do this for a simplicial cone, just look at the fundamental parallelepiped, and it's not very tall because presumably you're not doing this in a very high dimension. So I'm saying look at this three-dimensional parallelepiped and just count points in there by level. You do that, and you've solved the problem of computing lattice points for any dilate of the polytope. Okay? So that's a very useful proposition. Okay. So let's leave that proposition up. So now, here's a lemma that is going to look familiar to you, no doubt. It's also called homework 4 problem. What problem is it? The one about the polynomials. 4? Let's say that you have a function from the naturals to it doesn't matter to what. Let's say to the complex numbers, to the real numbers. It doesn't really matter. Okay. Then the following things are equivalent. F of n is a polynomial of degree d if and only if the generating function equals something like this, basically. It should equal some polynomial divided by 1 minus z to the d plus 1, where g of z is a polynomial of degree less than or equal to d, such that g of 1 is not 0. So probably, if you looked at your homework, there was one question that seemed to have nothing to do with the others, right? But hopefully this explains to you why this is a homework question. By the way, do you guys have any idea how to do this? Do you guys have some ideas about it? I mean, I'm sorry? Finite calculus. So if you know what finite calculus is, that's one way to do it.
So every polynomial counts a polytope.
Wow, that's fancy. It turns out that actually, let me give you guys a hint for this. We have time for a hint. So hint for the lemma. We prove this. Sum of let me make sure I get it right. We prove this sum from n equals 0 to infinity of n plus 1 to the d, or to the, let's say to the k, x to the n. Does this look familiar? Actually, that also looks familiar because it's another homework question. It's okay. So let me multiply by x. Okay. So this becomes 1 That means I probably have a typo here somewhere. I think this is what it is.
So you wrote Z's where you got, or you wrote K where you got C. It's D minus 1 and then
I had a D minus 1 and now it's a D. That's what it is, yeah. Okay? Now, you see, instead of n, let me use n plus 1. Okay? So this is equal to the sum of m to the k x to the m. You're just missing the first term, right? It goes from 1 to infinity. But then if you think about it, actually the 0th term, I mean, I can also just put a 0 here, because the term m equals 0 is 0 to the k, so it doesn't matter. And maybe instead of m, let me use n, so that it's more suggestive. N to the k, x to the n. And the point is that I've given you the generating function for n to the k. And that's the prototypical polynomial. Right? That's everybody's favorite polynomial in n is n to the something. Simplest polynomial. Okay? So in particular, this shows that for this polynomial, this is true, that you get a polynomial divided by 1 minus x to the plus 1. And that's my hint. Maybe I'll stop there. Okay. Okay. Now, what's the nice thing about this? The nice thing is that once you have proved this lemma, we have a theorem. Because you see, this Ehrhart series clearly satisfies this. You know, the denominator matches. The numerator is a polynomial of degree less than or equal to d. We have to check that g of 1 is not 0. What happens when you plug in z equal to 1 here? You get h0 plus h1 up to hd, and that's the number of lattice points in the fundamental parallelepiped. There's at least one, which is the origin, so this is not 0. So this lemma applies to this situation. Okay. So what am I saying here? Still might need this, I'm not sure. What am I saying here? I'm saying now the Ehrhart series is by definition the sum for n greater than or equal to 0 of L sub p of n z to the n. Or maybe let's use x's so that this matches. So by the proposition, this is g of z over 1 minus z to the d plus 1 with all the other conditions of the lemma holding. By the lemma, that means that this sequence is polynomial. Lp of n is polynomial. Okay. So I think I just did something behind your back, and you probably had no idea where I was heading. And now look what I have proved. What I have proved is that, remember what this is. This is the number of lattice points in n times p. And what I just showed to you in some kind of twisted way is that that's a polynomial. Okay? And well, as I told you, this is called the Ehrhart polynomial, and now you see why, because it is a polynomial. Okay? I'm sorry? And we know its degree, actually, because That's a very good point, because I shouldn't stop there. It is a polynomial of degree d. Okay. Of degree d. And this is what we call the Ehrhart polynomial. Okay? And so I hope that this will help you appreciate this machinery of generating functions, because at first it seems just kind of a very strange thing to do. It's kind of messy, at least when you're getting used to it. But it pays off. It pays off. Now, we have to be a little bit careful, because I just proved this for simplices, right? But I haven't proved it for arbitrary polytopes. So how do I do it? Can you give me a two-word proof? That's one. So theorem for any polytope, for any d polytope, P with integer coordinates, this thing is a polynomial of degree d. Okay. And the proof, again, just triangulate. Now, triangulate. One word. Period. End of proof. I mean, again, let me acknowledge that it's a bit of an understatement. It's a bit of an oversimplification. But it's basically true, because if you want to compute the lattice points in a pentagon and its dilates, then what you're going to say is count, you're going to triangulate in whatever way you want. We know there's at least one. By the way, so now you also see why we even bothered proving that triangulations existed, and the proof was strange, this regular triangulation business. But we needed to know that we can do this. Okay? So we're saying now, add this, plus this, plus this. Okay? Is that it? Well, no, I overcounted, right? Because I overcounted this diagonal, so I should subtract it. And I overcounted this diagonal. Am I done?
No, you gotta add that to the point.
I overcounted. I overcorrected, because now this point I subtracted it twice, so now I'm not counting it. Is that right? I added it here. I added it here. I added it here, so that's 3 times. Then I subtracted it once. I subtracted it twice, so I counted it once. So actually, this is it. But that's precisely the kind of overcounting you have to be careful about. Okay. Now, what's the point? The point is polynomial plus polynomial plus polynomial minus polynomial minus polynomial. That's a polynomial. Okay. And now that's almost the proof, but there's a little bit. I'm sorry?
You have to add back in those other 2 points, the bottom 2 points. Because it's different.
No, but this point I'm added it twice and subtracting it once, so it's fine. This requires care. That's the moral of the story. But it can be done, and you're going to do it in the homework, by the way. So now, actually, there is another tiny detail here, which is that I'm claiming it's a polynomial of degree d. Okay. So here I'm saying this is quadratic plus quadratic plus quadratic minus linear minus linear. Is that quadratic? Well, it's at most quadratic. But is it possible that the quadratic term canceled out. It turns out that, and I'll prove it next time, that the leading coefficient of the Ehrhart polynomial is the volume of the polytope, which means that it's positive. And because it's positive, then it's not going to cancel out. So actually, that's something nice for you guys to think about. Why is it that the leading coefficient of this polynomial is always the volume of the polytope? Think about that. We'll argue next time why that is, because so far we don't know what volume is, actually. It's the first time that I say the word volume in this class. But you know what volume is, so think about it, and then you'll see that it's true. Okay? All right.